Hi everyone. I want to talk about special relativity now, a little bit of a change in subject. But the foundation of special relativity is really in electromagnetic theory. And so there's a story, I don't know if it's apocryphal or not, but there's a story about Einstein as a teenager kind of investigating, understanding electromagnetic theory. At the time that would have been the forefront of physics. It would have been like, someone interested in string theory today, right? So that was like the bleeding edge of physics. And so he was interested in all this stuff. And so he kind of thought about the idea, what if I take a flashlight? He didn't have flashlights, but imagine he had a flashlight and you shine the light, and suppose I'm very fast, I'm Usain Bolt, right? And I can run super fast, and suppose I can run at the speed of light and catch up to the light, and I look at it, and I say, hey, what would I see? And so what Einstein realized is if you catch up to the light wave, essentially the electromagnetic fields stop. Now, that's impossible, because Maxwell's equations require the electric and magnetic fields to continue to oscillate. Otherwise, they won't feed one another. So this produces kind of a fundamental contradiction that, essentially means that Maxwell's equations fall apart if we can catch up to a light ray. Now, this kind of stuck in the back of Einstein's mind. He thought about it and mulled over it for a while. And, fundamentally it shows that there is a deep contradiction between Maxwell's equations and Newton's laws of motion. Now, if you're a betting man or woman, I think you would bet on Newton in this case, because, this is the forefront of physics. And so, there must be something wrong, something that Maxwell missed. Maxwell himself discovered there's something that Ampere missed, so there must be something more to it. And I think most physicists were willing to bet that direction. Einstein, however, had the guts to ask the question, what if Newton's wrong? What if there's something fundamentally wrong about our notions of motion? Maybe I cannot catch up to a light beam, and that's in fact where we stand today. It's a common complaint about relativity that you cannot go faster than light. Well, they used to say that about the speed of sound, but we found a way to break the speed of sound. There is a fundamental difference between the speed of sound and the speed of light, and it is physically impossible to move faster than the speed of light. That does not mean that we may not someday be able to transport something from here to there in a very short time frame. But we will not be able to move from A to B faster than the speed of light. And that's what the special theory of relativity tells us. So, what Einstein realized as he thought more about this was that at the fundamental level, we have to reconsider how we think about speed, and the components of speed, which are distance and time. We have to think about space and time differently. And that is the fundamental paradigm shift that you have to undergo if you want to really understand the special theory of relativity. One example is this velocity addition formula here. So this, forget this denominator for a second. The way we imagine velocities combined together in kind of an everyday way, if I'm on a boat, that's going down a river, and I'm walking along the boat, and someone on the shore looks at me and figures, how fast is that guy moving? Well, basically you take the speed of the boat, add it to the speed of the person walking, and that's the total velocity relative to the shoreline, right? You just add the two, simple. That's all there is to it. However, Einstein discovered that you have to add this denominator to the formula in order to get it to work, in order to get the whole theory to work together. Now, I'm not describing where this formula comes from yet. I'm just asserting the fact right now that velocities do not combine the way Newton taught us. They combine this way. This is Einstein's way of combining them. The interesting thing about this formula is no matter how fast these v's are, as long as they're less than light, this total is always less than the speed of light as well. And it's because as these get larger, the denominator gets larger. The speed of light is sitting here. And so if I have two objects, if I have a flashlight that shines another flashlight, you've got a light beam coming from another light beam, two speeds of light, add these together, that's going to go at the speed of light. So no matter how fast things are going, you cannot get something that moves faster than the speed of light.